Hello students, today we are going to see the main body of the Lagranges theorem. In our previous video, we have seen what is COSET and the two important lemmas that we are going to use in this main body have seen in previous video. If you have not seen the previous video, please go to that video first, understand that concept, then come back to this main body. Okay. Statement of the Lagranges theorem. If G is the finite group and H is a subgroup of G, then order of H is a divisor of order of G. For example, we have a big group of 1000 elements and it has a subgroup H. What this Lagrange theorem says is the number of elements in subgroup divides that 1000. We are going to prove that. Let's see. You can see that it's a big theorem, right? Here I have written the step-by-step process to understand. Ask a question, state and prove Lagrange's theorem in your examination. You have to mind these 4 steps so that you can write the whole theorem without any trouble. Let's see. Come here. The first, you can notice that what we will define order of G equal to n and order of H equal to m. This is the step 1. In the second step, we will use lemma 10, what we have already studied. And we will prove that every left coset has m elements. Step 3, we will use lemma 9 and we will prove that k distinct left cosets will be there in G. Finally, we will prove the order of H is the divisor of order of G. These are the 4 steps we are going to see here. Let's see, come here. First step. Suppose that G is the finite group of order n and let H be the subgroup of G in such a way that order of H is m. Can you see that? First step is over. Second step. We know by lemma 10, we have already studied, any 2 left cosets of H in G has same number of elements. We have studied in lemma 10. Okay, you can notice that suppose it is a group G and it is a subgroup H. You find some A here and make one left coset. What is the left coset? AH, right? AH. Suppose this H has some 50 elements. Let us assume that. Then this AH will be AH1, AH2 like this, AH50. All these 50 elements, maybe it may be some G1, G2, it is G50, it will be here. You can notice that somewhere here E is there. If you select that E, and what will be left coset generated by E? What is EH? It will be EH1, right? EH1 is again H1. EH2 is again H2. EH50 is again H50. This left coset generated by E is again H. So H itself is a left coset of H. It is a special left coset which is also a subgroup, whereas all other left cosets are not subgroups. Now come here. That's what he is telling. See, since H is EH, this itself is a left coset of order m. Then I have taken 50. That 50 is our m here. Any left coset of H has m elements. Then obviously it will also having m elements. This will also having m elements. Any left coset, because that's what our lemma 10 says, right? Our lemma says any 2 left coset have same number of elements. Okay. Since G is finite, there are only finite number of left. We will know that G has only finite number of elements. It cannot contain infinite number of left cosets, right? For example, if we have a big mass, we are making, it's a finite mass. We are making that mass into small groups. Can you get infinite number of groups? It's not possible, right? We will be getting finite number of groups. Same way. We know, okay, since G is finite, there are only finite number of left cosets of it in. Now step 2 is over. Now we are using step 3. We know by lemma 9 that any 2 left cosets are either identical or disjoint. So now we understood that it has finite number of left cosets and there won't be any overlappings. Two left coset won't be like this. If it is possible, you can find so many left cosets overlapping with each other. It's not possible. It's not possible. These left cosets will be either identical, same, or they will be disjoint. So it should be a finite number, the number of left cosets. So let K be the number of distinct left cosets of H in G. Now you can notice that I am generating AH, right? I am generating left coset AH. All the 50 elements I have put here. Somewhere here, because that H is a subgroup, it has E. E will be here. What is AE? AE is again A. So, in a left coset generated by A will be there. In a left coset generated by B, in BH, B will be there. Why? H has identity element E. B is again B. Somewhere here B will be there. Yes. Okay. Since A belonging to AH, for every A belonging to G, every element of G must be in any left coset. It may consist of 1000 elements. You just generate 1000 left cosets. Obviously what we are going to get, either, for example, this BH has 50 elements. All the left cosets generated by these 50 elements will be on BH only. It won't go outside. All the elements generated by this AH is again on AH only. It won't go outside. Therefore, the elements of G are distributed into K cosets. We can notice that it is just A1H, A2H, A3H. The whole set distributed into equal number of small cosets. Therefore, the elements of G are distributed into K cosets with M elements in each coset. So, this N is K times equal M. So, K is N divided by M. N is order of G. H is M is order of H. So, we can notice that number of elements in G is divided by number of elements in H, and we are getting a whole number. Full number. It's not decimal part. There is no decimal part. So, order of H is a perfect divisor of order of G. This is the proof of the theorem. Thank you.